Okay, let's look at theorem 3.6 and its corollaries in section 3.2, which is about the rank of a matrix and matrix inverses. So let A be an m by n matrix of rank R. Then we conclude that that rank is less than the rows, less than the columns, less than or equal to the rows, less than or equal to the columns. And by means of finitely many elementary row and column operations, A can be transformed into the matrix D that has the identity matrix in the upper left, zero matrices in the upper right, lower left, and lower right. So these are zero matrices. Another way of saying that is DII is 1. These are 1 entries, and every for the first R of them, and the rest are zeros. Okay? So this proof is sort of a long proof, and many pieces of it sort of go into the homework. So if A equals an entirely zero matrix, then the rank is 0 by exercise 3, which you will prove. Isn't it great that you'll take care of it? Otherwise, and that's not hard to see, this matrix is all 0. A is equal to D, and hopefully you can establish that the rank is 0 indeed. Otherwise, R is greater than or equal to 1. In particular, every matrix has a non-zero entry, which is handy. Okay, now we will do induction on M, the number of rows in the matrix. So if M equals 1, okay, the matrix is going to look like sort of a list of entries. You know, you have A11, A12, out to A1n, right? Some entry non-zero, right? If it has rank greater than or equal to 1, something is non-zero. Using at most one type 1 column operation, that's swapping 2 rows. You can move that non-zero entry to the front, and one type 2 column operation. Remember, that's a scalar. You can rescale that non-zero entry to 1. Get a matrix of form 1 star star something there, right? Okay, now using at most n minus 1 type 3 column ops, right? What is that? You can add any multiple of column 1 to all the rest. Change to form D equals 1, 0, 0, 0, right? Add whatever that entry is there, and then it'll get to be all zeros, just as we need. Okay, so that takes care of the base case. Now, assume true for M less than 1, let's say M minus 1, and we will show for M. Okay, so how's this going to work? Well, unfortunately, now we have to worry about the n. If n equals 1, okay, so now we're going to think about something where there's just one A equals A 1, 1, A, 2, 1, down to A, M1. The theorem holds and you will prove this in exercise 10, okay? It's fairly straightforward. It's a whole lot like this right here for the column, okay? So now, if n is greater than 1, okay, A is non-zero, so you've got some non-zero entry by at most one column and one type 1 column and one type 1 row. Those are the swaps. Type 1 row operation. Move the non-zero entry to the 1, 1 position. And use a type 2 operation, frankly it can be a row or a column operation, to make that entry 1. Okay, so we've got a 1 in that upper left, far upper left position, right? Now remember what we did right here, we used those type 3 column operations to make all of the other entries 0. Now use up to n minus 1 type 3 column ops. And you can do the same thing with row operations. M minus 1 up to M minus 1 type 3 row ops to convert the matrix to the form 1, 0, 0, 0, 0, 0, right? Those are what the row operations are going to do, those type 3 row operations. 0, 0, 0, 0, 0. I should put dots here just to be clear. We have no idea how big this is. Dot, 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 dot. And then we have some matrix here. Let us call it B prime. So if this is B, this is B prime. B prime is an M minus 1 by N minus 1 matrix and can be converted to the desired form by induction, right? This is a matrix of smaller form, okay? So the only thing left to notice is that this can be converted by finitely many row operations. This is finitely many row operations. But one should notice a row operation on B, or column operation, is directly equivalent to a row or column operation on B prime. So if you needed finitely many operations there to get it in the form of D, you can just apply those to B, then by induction right? D equals 1, 0, 0, 0, 0, 0, 0, and you get some sort of D prime here of the desired form. With D prime of desired form. Okay, so hopefully that makes clear. And this is a pretty powerful form because when you're looking at a matrix of this form, it's much easier to see here, oh, this has rank 3, right? It has 1s in the diagonal into that far. And there's actually 3 corollaries that sort of go with this and make it even more powerful. The first corollary says, hey, if you have an n by n matrix, there's an m by n matrix on the left and an n by n matrix on the right, such that D equals that. Well, remember, this is a corollary, not a theorem, because remember, we had finitely many row operations, elementary row operations, I should say, that we applied to D. Well, finitely many row operations that you apply to D correspond to finitely many elementary matrix multiplications. On the left. In other words, if you took D and you had sort of E1, E2 out to EK, those are in one-to-one correspondence with elementary row operations. And similarly, you have that same correspondence with elementary column operations and right multiplication by elementary matrices. And so you've got sort of E1 prime, E2 prime, I don't know what subscript we should use there, EK prime. And so you get all of this equals, wait, I guess I was supposed to start on A and say, yes, I do that to get to D. And that's what was required, right? Now, I think I'm going to skip to what the book calls corollary 3. Notice that every invertible matrix is the product of elementary matrices. So if you have something like that, and D, if it's an invertible matrix, what's its rank? Its rank is n, which is equal to m. So D is actually the identity matrix, right? So you have something like EK, E2, EK minus 1, down to E1, A, E1 prime, out to EK prime, equals the identity matrix. Well, then what should we do here? I guess I should multiply on the left by the inverse of these, which is also elementary matrices, right? The inverse of an elementary matrix is an elementary matrix. Multiply on the left by those, multiply on the right by the inverses of those. So A equals, let's see, if we multiplied on the left by, what should it be? It should be E1 inverse, E2 inverse, out to EK inverse. Notice if we multiply that out there, life will be good. Then we'd have the identity matrix here, but that sort of disappears. And then over here, we have EK prime inverse. Maybe my notation isn't the best, but these are all elementary matrices, E1 prime inverse. And so, yeah, it's pretty easy to see that a matrix like this, those elementary row and column operations really correspond to elementary matrices. And it's nice to know you can get everything in this terms. We mechanically have been doing this, but it's nice to know every invertible matrix must be writable like that. One last corollary. it says the rank of A transpose is equal to the rank of A. Just notice that if you applied a transpose to everything in sight here, what would happen? Well, elementary matrices transposed are elementary matrices. Elementary column operations applied to the transpose would be elementary row operations, and so on. We've looked at this previously, but if you look at the rank of a matrix in form D, right, the rank of A corresponds to now the number of linearly independent rows, right? All of these rows are 0 rows, right? Sorry, I guess I should be doing rows. All of these rows are 0 rows, right down here, 0, 0, 0, right? The only ones that aren't are these, and they're all clearly linearly independent rows. And the rows or the columns generate spaces of the same dimension. And that's pretty clear here if the rows are 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. And so you can count them up. And of course, the rank is going to be A, which in the theorem itself was R. I hope that's helpful.